In this video, what we're going to do is we're going to unpack Ampere's law a little bit more. So I've written Ampere's law up here in the right-hand corner of the board. And what we're going to do is sort of separately take the left-hand side and the right-hand side to understand them in some detail. So what we're going to do in this video is talk a little bit about this left-hand side of the equation, namely the circulation integral of B dot dl, going around the loop and adding up all the little pieces here. So to understand that, what we're going to do is we're going to take first a current that comes out of the board. So think about a wire coming out of the board, and there's some current that it's carrying. In this case, the magnetic field at some location points like this. So it sort of circulates around in this fashion. And at any given distance from the wire, at the same distance from the center of the wire, the magnetic field is the same magnitude, and it points in this sort of direction going around the wire. So for a given choice of this distance, we're going to end up calculating something that has to do with the magnetic field at that location and the, if you will, the circumference or the perimeter of the loop that we've chosen. If instead we decided to calculate this in a slightly different way, we pick a different location, so maybe we pick something a little farther away, those magnetic field vectors are going to be quite a bit smaller. As we go around, but the perimeter of the loop that we go around is larger, right? So there's some play here associated with the specific magnetic field and the perimeter or the loop that we're going around, right? And they as we get farther away from the source, the field goes down, but the loop, the perimeter of the loop, gets bigger, right? And so they play off of each other exactly so that the total amount of circulation, that is what this calculation gives you, is going to be the same, namely that it'll be equal to the enclosed amount of current times mu zero. So this is quite interesting. It tells you that in most of the cases that we're going to have, because we're going to deal with steady currents, that this circulation is going to be equal to some sort of constant. And so the question is, okay, how do we go about doing that calculation, right? So what I'll do is I'll get rid of the exterior ones here, the ones that are farther away, and I will specifically label these as magnetic field vectors that kind of go around. So a smart choice of loop is one that goes in the same direction as your magnetic field. And the reason for choosing that is because then the dot product that you have on this left-hand side is really straightforward. So if I were to choose a path that follows the magnetic field, that is, here's my dl vector, here's my dl vector, here it is, all the way around, that is, it sort of exactly follows the magnetic field, then my calculation that's associated with B dot dl simplifies to B dl, namely because they both point in the exact same direction. What's also really nice is if you can argue, like we did with the Gauss's law situation, that the magnetic field is then a constant over your choice of perimeter, over your choice of loop, then you can pull that magnetic field outside of the integral. And that's true for this case. We know that at any given distance, r, the magnetic field is going to have a constant value in terms of its magnitude, and we've already dealt with the direction through this dot product. So in fact, this simplifies even further. That is that we are going to integrate just to find the perimeter of the loop. In this case, it is a circular loop because it follows the circular pattern of the magnetic field. And so the result will be, in this case, B times the perimeter of that loop, which is the magnetic field times 2 pi r. Now, this is only the case for this particular choice of loop. We chose an Amperian loop that followed the direction of the magnetic field. And in this case, the magnetic field direction points around the current. In other cases, in other situations you might be in, the magnetic field doesn't necessarily point in this sort of direction. And so you have to be careful about how you choose the loop so that you can both deal with the fact that you want the magnetic field and the direction in which you're calculating the integral to point in the same way, so you can deal with the dot product simply, and so that the magnetic field is a constant, so you can pull it out. And then just deal with the fact that the magnetic field times the perimeter is what you have as the left-hand side result. Now, this goes back to sort of the idea of Gauss's law, in that Gauss's law is always true. It applies to every single problem that you've ever seen with electric charge, but it's not always useful. It's only useful when you can actually deal with the dot product and pull out the electric field as a constant in the integral. The same is true for Ampere's law. Ampere's law is always true. That is, that the integral associated with the magnetic field over any loop is equal to the charge enclosed, or sorry, the current enclosed times mu naught. But it is not always useful for dealing with problems, because you can't always calculate this dot product simply and pull out the magnetic field. So in this video, what we did was we talked a lot about the details of what goes on the left-hand side, and we're going to use that to finish analyzing this problem to get a result that we had previously that tells us about a long straight wire.